Hey, everybody. It's Wednesday, May 19th. As you can see here in the aim today, our goal for today's video is to review the last two free response questions we are going to look at for the year. We have finally made it to the last video reviewing free response questions before the AP test. These are both experimental design questions, as you should know if you did this assignment yesterday already, so I'm just going to jump right into it. The first problem here says a company selling a type of spring makes the following claim. The elastic potential energy that the spring is capable of storing for a given compression distance does not decrease, even after the spring compresses and or stretches hundreds of times. The students in a physics class have decided to test the company's claim. And part A has two individual subparts. It says state a basic physics principle or law that the students could use in designing an experiment to test the company's claim. And then part 2 says using the principle or law stated in part A1, determine an equation for the elastic potential energy stored in the spring in terms of quantities that can be obtained from measurements made with the equipment usually found at a school physics laboratory. Now, there are a lot of ways that you could have interpreted this question. I decided in my sample answer here to just take the most straightforward approach, which is basically to just measure the elastic potential energy using the idea of conservation of energy. Now, there are a lot of ways you could potentially go about this, though. I think it's important to realize whether you realize this initially or not. This problem here says the elastic potential energy that the spring is capable of storing for a given compression distance, does not decrease even after the spring compresses or stretches hundreds of times. It's important to realize if you're using the elastic potential energy equation, then essentially what they're really saying here is that the spring constant stays constant. If you set the x, they're saying, the elastic potential energy, US, will remain the same. That's only possible if the spring constant remains constant, as you all probably know it should by now, or at least I freaking hope so. So it's important to realize I'm not going to confront that issue directly because I thought, it required a little more explaining on the back end to go that way. But it's important to realize that's a perfectly reasonable way to go about this problem as well. The spring potential energy or the elastic potential energy that the spring would store can only stay constant if the spring constant is constant when the thing is being stretched or compressed a given compression distance. So it says here in part A1, state a basic physics principle that the student or law that the students could use in designing an experiment to test the company's claim. And to me, the basic physics principle or law that you're supposed to apply here was obvious. The principle that can be used to determine if the elastic potential energy stored in the spring is the same when the spring is compressed hundreds of times is conservation of energy. Now, there were a number of ways you could have done this. What I thought of, what really made the most sense to me, was to just use the spring to shoot something. Now, whether you shoot it horizontally or whether you shoot it vertically is entirely up to you. There are a lot of ways you could do this. You could shoot the object horizontally, have it pass through some sort of device which is capable of measuring its velocity, and do it the kinetic energy route. You could shoot the thing straight up in the air and just use a meter stick to measure its maximum height and do it that way. I decided for the basic details of this experiment to just go through and talk about the basic conservation of energy approach. So what I'm going to say here is the initial spring potential energy is equal to the final kinetic energy. Once the spring is totally decompressed, it's just going to shoot an object. And that means the equation here, notice, just works out to be real simple. We get 1/2 mv max squared. And so it's important to realize, I actually really like this part that they wanted you to derive this equation in the beginning, because it sort of highlights this point that I've been really trying to hammer home the last bunch of weeks, which is the equation is the key thing you're supposed to pay attention to in an experimental design question. If that's the equation, that equation tells us everything we have to measure. Take a second to pause this video here and write that down. When you hit play, take a look at the scoring guide. All right, moving on to the scoring guide here. Both of these parts together were really only worth 1 point. It says for a valid equation or valid equations in A2 that are consistent with A1 and that includes the elastic potential energy stored in the spring. Now, I think it's weird that it says and that includes the elastic potential energy stored in the spring, and then they showed this equation. Notice the first thing was just a literal measurement of the elastic potential energy using the equation 1/2 kx squared. That would presumably involve you in measuring the spring constant over and over and over again. They have the equation that I just used using the conservation of energy with the kinetic energy approach. I think it's weird that they wrote this like this, honestly. I would think the equation would end up looking like this. If you did that, though, that is a totally reasonable way to approach the problem. You just have to take the spring, compress it, and then shoot an object straight up in the air. That's the idea. Take a second to pause this video here. Make sure you understand all aspects of the scoring guide, and when you hit play, we'll move on. All right, moving on to part B here. Part B says, design an experimental procedure the students could use to collect the data needed to test the company's claim. Assume equipment usually found at a school physics laboratory is available. The table below lists the quantities and associated symbols that would be measured in your experiment and the equipment used to measure them. Also lists the equipment that would be used to measure each quantity, and then you do not need to fill in every row, blah, blah, blah. So the first thing we should say has to be measured, looking at this equation, is we're going to have to measure the maximum velocity of the object. And so I'm going to write here max velocity, and I'm going to use the symbol Vmax. And I'm going to say here that the equipment I'm going to use for this measurement is a photo gate. Once I shoot an object like a ball from the spring, I could just aim the object in such a way that the ball is going to pass right through a photo gate. Obviously, you can also use a motion sensor. Either way would be totally fine. I think the key thing to remember is that a motion sensor can only be used to measure things in a straight line. And so you would have to make sure you fixed the spring to some object and then compressed it, shot the object, and then used the motion sensor down here to measure the object's maximum velocity. It can be done. We're also going to want to measure the mass of the object, whichever object we're using here, and we'll do that with a triple beam balance. And the last thing we have to measure, and I hope you realize this, it's actually not in the equation. Notice the equation that we used here is US naught, the spring potential energy in the beginning, equal to 1/2 mv squared. But notice the problem said the thing needs to maintain the same elastic potential energy for a given compression distance. So effectively what we're saying here then is we have to set the compression distance in the beginning and compress the spring that amount every single time. That's the idea. Obviously, we can't determine if the potential energy stays the same if we change the compression distance, because definitionally, the energy stored by the spring is going to change when the compression distance changes. And so we're going to use a meter stick to measure this compression distance just so we can keep that the same every time. Take a second to pause this video here and write that down. Of course, checking this against whatever list you might have written. Obviously, if you used a different procedure, then you're going to have a different list. And when you hit play, move on to the next part. All right, now the scoring guide for this section goes with this later part here that continues with part B. And so I'll show you that at the end. This part here says, describe the overall procedure to be used, referring to the table. Provide enough detail so another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. As needed, use the symbols defined in the table and/or a simple diagram of the setup. This is what I wrote. It's a lot. I said, in order to test the company's claim, we can use a meter stick, a triple beam balance, and a photo gate to measure the spring's compression distance, the mass of a ball will launch from the spring, and the initial velocity of the ball, respectively. This would be the maximum velocity of the ball here after it's launched, of course. It says the meter stick will be used to measure the spring's compression distance in order to ensure that we are keeping this constant every time we use it to launch the ball, because the energy stored in the spring is proportional to the square of the compression distance. The triple beam balanced will be used to measure the ball's mass at the start of the experiment. The photo gate will be positioned at the end of the spring to measure the velocity of the ball when it's launched from the spring. At the beginning, we'll launch the ball 5 times with the spring compressed the same distance, measuring its launch velocity every time and averaging them together to determine our first average launch velocity. So we want to make sure that we're reducing experimental uncertainty, and to do that, we'll just launch it a bunch of times. Now I wrote here, afterwards, we'll compress the spring 100 times. Remember, it said it's going to stay constant when the spring is stretched or compressed hundreds of times. So we do our first 5 launches, and that's our first data point. Then we compress the spring 100 times. You could just sit there probably with your fingers and just compress it 1, 2, 3, 4, 5, 6, 7. It's probably not going to be that hard, depending on obviously what the spring constant is, but we'll assume it'll be a normal spring that actually can be compressed reasonably easy in this amount of time. I wrote here then afterwards, I already said that. Afterwards, we'll compress the spring hundreds of times. We'll repeat the launches at the same compression distance measured with the meter stick, measuring the velocity of the ball 5 times to determine our second average launch velocity. We'll compress the spring 100 more times and then repeat this procedure until we have obtained 5 average launch velocities. That's the idea. We get a bunch of data points, we compress the spring 100 times, we get 5 more data points, average them together, and then, of course, what we should have here is 5 separate launch velocities. Of course, we can use that ultimately to calculate 5 separate elastic potential energies. Take a second to pause this video here and write that down. When you hit play, we'll move on. All right, moving on to the scoring guide here. You got 1 point for the measurements and equipment list, and it said for listing relevant, appropriate equipment that matches the measured quantities. Okay. You got 1 point for in the procedure section for a plausible or practical way to directly or indirectly determine the stored energy in the spring or the spring constant of the spring. Notice I was mentioning that at the beginning, that the only way the energy is going to stay the same is if the spring constant stays the same. So you can use that as like a sort of proxy measurement to get your stored energy in the spring. 1 point for compressing and or stretching the spring multiple or hundreds of times between the initial and final measurements. 1 point for including both initial and final measurements so that the stored energy can be compared. And then 1 point for attempting to reduce uncertainty, for example, multiple trials with either one spring or multiple springs. Now, the scoring guide gave a series of example procedures that I want to show you here in a second. So take a second to pause this video here, look this over, and make sure you really understand all aspects of the scoring guide. And when you hit play, we'll take a look at those examples. All right, so example procedure 1 effectively uses the procedure I used. You had your spring compression being measured with your meter stick, your maximum velocity Vmax being measured with the motion sensor. It's weird that they didn't put the mass in this list. I don't really get that. It says here, attach the spring to a wall horizontally, push a block into the spring, compressing the spring at displacement D, measure the displacement D with a meter stick, release the block, and use the motion sensor to record the block's maximum velocity Vmax. Of course, that'll totally work like the photo gate would, so it's totally fine. It says repeat the experiment to verify the maximum velocity, compress the spring from equilibrium distance D back to equilibrium hundreds of times, and then repeat these displacement and maximum velocity measurements. Take a second to pause this video here and look this over if you want. And when you hit play, we'll move on to example 2. All right, moving on to example 2 here. We have the spring compression being measured here by a meter stick, of course, and then the maximum compression force being measured with a force sensor. And it says attach the spring horizontally to a wall. Apply a force F max to compress the spring at displacement D from equilibrium. Measure D with a meter stick and F max with a force sensor. Relax the spring and repeat the experiment to confirm F max. Notice there, they're just doing 2 trials. Then it says to compress the spring from equilibrium to displacement D and back to equilibrium hundreds of times, and then repeat these measurements. Notice, basically, they're measuring F and X in the equation F equals Kx, which is going to give them enough information to be able to determine the spring constant. Take a second to pause this video here if you'd like to give this a second look. And when you hit play, we'll move on to part C. All right, moving on to part C here, it says explain how the students should analyze the data to determine whether the company's claim is true. In other words, whether the energy stored by the spring for a given compression distance does not decrease after the spring has compressed or stretched hundreds of times. So what I wrote here is, since our experiment is determining the average launch velocity at a fixed compression distance, we can use conservation of energy to determine the maximum kinetic energy of the ball after it is launched by the spring using the equation K equals 1/2 mv squared. Since the maximum kinetic energy is equal to the elastic potential energy, by finding the maximum kinetic energy, we've determined the elastic potential energy. Since we compressed the spring hundreds of times between launches, If the maximum kinetic energy, and thus the elastic potential energy, is the same over all 5 launches, then we will have shown that the elastic potential energy stays the same over hundreds of compressions. I do want to fix something here. And it doesn't actually say this in the scoring guide, and so I don't think it's that big of a deal, but it has come up in other scoring guides, and I think it is an important thing to mention. It's important to realize if you did this experiment and you obtained 5 values for your elastic potential energy, and you got like 1.605 joules, 1.604 joules, 1.606, 1.603, 1.602, you might look at that and say, oh, yeah, well, this is definitely decreasing. Look at the energy, except for that, second trial here, all the energy amounts are going down. It's important to realize that if you get a variation like that in the 3rd decimal place, only with 5 trials, that's not really enough evidence to be able to say that the elastic potential energy decreased. And so I want to add something to here because I wrote, since we compress the spring hundreds of times between launches, if the maximum kinetic energy and thus the elastic potential energy is the same over all 5 launches, and I'm going to write here comma, or I guess I'll write it in parentheses, within experimental uncertainty. That's an important point here, I think, because, there are always going to be random errors involved in any experiment. And so if you were doing an experiment to show the acceleration due to gravity in your classroom is constant, and you made 5 measurements, it got 9.8 and 9.7 and 9.9 and 9.8 and 9.10 or 9.10, whatever. You would hopefully realize that, yeah, those are pretty much right on. There are going to be errors involved in any experiment that is going to make the numbers slightly different. And I think that's an important thing to remember. Within experimental uncertainty is going to be a phrase, depending on the experiment, that can save you a point. Because if you talk about the things being meaningfully different, that's really what the point of the experiment is getting at. And I think that's a crucial thing to remember for the test. Take a second to pause this video here and write that down, giving it a good second look. And when you hit play, take a look at the scoring guide. All right, taking a look at the scoring guide here, you got 1 point for explaining how to compare the initial elastic spring potential energy to the final spring potential energy after many trials, or a plausible alternative to quantify if the energy stored by the spring for a given compression distance does not decrease after the spring is compressed and or stretched hundreds of times. And then 1 point for how the comparison would confirm or refute the hypothesis. Take a second to pause this video here, look that over, because there are 2 sample answers I want to show you here after this. And when you hit play, we'll take a look at those. All right, let's take a look at these sample answers here real quick. Example analysis 1 is when the spring is compressed and comes back to equilibrium, all the stored elastic potential energy is transferred to the kinetic energy of the block, causing the block to reach maximum velocity. If the Vmax of the block before and after the hundreds of stretches is the same, then the stored elastic potential energy is the same, and the company's claim is true. If you remember, when I said in the beginning, it's kind of weird that they didn't put the mass. Well, that's the reason why. You don't actually have to calculate the full kinetic energy because we know if the kinetic energy is going to be the same or different, I guess, it's because the velocity is the same or different. It's all about the velocity. The mass of an object is obviously not going to change when you're launching it from a spring. So that's how they get around that. And of course, it says if the maximum velocity is the same, then the company's claim is true. And the basic idea is that conservation of energy tells you that. Take a second to pause this video here if you want to give this a second look. When you hit play, we'll move on to example analysis number 2. All right, moving on here. Example analysis number 2 says the work done on the spring is equal to the average applied force, which is half of F max times the displacement from equilibrium. The work done is also equivalent to the elastic potential energy stored in the spring. If F max remains the same for same displacement after several hundred stretches, then the elastic potential energy is the same and the company's claim is true. Again, I think both of these analyses are kind of lame. They're not really taking it to the last step, by actually doing full calculations to confirm, but it's good enough. Notice if the energy stored in the spring was going to decrease, that means the spring constant would decrease, which means the force needed to compress the spring a certain distance is going to change. That's the idea. And so because it doesn't, or I should say if it doesn't, then we would know that the company's claim is true. And you should know, the company's claim is probably going to be true unless it's a really crappy spring, and the metal is going to get bent so out of shape that it's just not going to work anymore. Take a second to pause this video here and give this a second look if you want. When you hit play, we'll move on to part D. All right, moving on to part D. Part D says the students also investigate two springs, spring A and spring B, made by another company. The students hang spring A vertically, attaching blocks of various known masses from the bottom end of the spring and measuring the total length of the spring for each block. The students graph the spring length as a function of hanging mass and draw the line of best fit as shown below. It says the students follow the same procedure using spring B, which has the same equilibrium length as spring A, but stores more energy than spring A for a given displacement. On the graph above, sketch what the line of best fit could look like for the data obtained using spring B. Now, there are a couple of things in there that you're going to want to pay attention to. The first thing is that it has the same equilibrium length. And so that means when the hanging mass is 0, this thing is going to have a length of 25 meters. That's going to be the first point. This question is really a question about, is the slope going to be larger, smaller, or the same? And I hope everybody realizes by this thing saying it stores more energy than spring A for a given displacement means the slope is going to be the same. Now, let's really investigate what that means. Well, if it stores more energy than spring A for a given displacement, well, then what does that actually tell you? Well, it tells you the stored energy is proportional to the spring constant. And so if there's more stored energy, then we're going to get a higher spring constant. Question is, how do we represent that here on this graph? Notice this is a graph of spring length versus mass. And so think about what the spring constant means. A higher spring constant means this thing is harder to stretch. And so for a hanging mass of 50, let's say, instead of stretching to whatever distance that is, this spring is harder to stretch. It's going to be less and less and less and less at every turn. Of course, you want to make sure this thing is linear, and it's really hard to draw straight lines on this, using this digital pen. So I'm actually just going to erase all these data points, but hopefully you get the idea. Because this spring is harder to stretch, the basic reason why this graph has a lower slope than the other spring is because it's not going to stretch as much then when the same amount of mass is applied. Another way you could look at it, which is actually the way I thought about it. Honestly, the reason why I just said what I did is because I figured maybe you guys wouldn't understand the way I thought about it. The way I think about it is if we take the hanging mass and we just multiply it by g, the acceleration due to gravity, then this is going to be the weight, which is equal to the spring force. And when we take the spring force versus the stretch, the slope is equal to k. And so because this graph is reversed, instead of being the spring force versus x, it's x versus the spring force, or at least something like the spring force, then that means the slope here, keeping in mind if we multiplied this by g, the slope would be equal to the inverse of k. Here, instead of the slope being equal to the inverse of k, it's inversely proportional to k, we can say. Of course, you have to work in the fact that all of these x values need to be multiplied by g, but that's the idea. I see this as needing to have a smaller slope because the slope is inversely proportional to k. Take a second to pause this video here. Write that down. When you hit play, take a look at the scoring guide. All right, take a look at the scoring guide here. You got 1 point for a curve starting at 0, 25. And of course, that should make sense because they did tell you it has the same length. You got 1 point for a straight line with a positive slope. And you got 1 point for a line with a smaller slope than the original best fit line, regardless of vertical axis intercept. So even if you didn't get this point, you could have got 2 out of 3 if you just made it a smaller slope, of course, with a straight line as well. Take a second to pause this video here. Write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, moving on to the last part here. It says the students attach a 100-gram block to spring B and let it hang at rest. The students pull the block down by 1 centimeter, release it, and measure the time interval delta t for 1 oscillation. The students then repeat the procedure, but pull the block down by 2 centimeters instead of 1 centimeter. For which initial displacement, if either, is the time interval delta t greater? Well, according to the equation for the period of a spring is equal to 2 pi times the square root of m over k. And so the period has no relation to the amplitude. The time interval is the same for both. Notice by pulling the thing down from 1 centimeter to 2 centimeter, the only thing they're changing is the amplitude. So I wrote here, the period is the same in both cases. According to the equation for the period of a spring, period equals 2 pi times the square root of m over k, the period of the oscillation is directly proportional to the square root of the mass and inversely proportional to the spring constant. Since the amplitude is not in the equation, we know that the amplitude has no effect on the period of the oscillation. Since the only thing changing in the system was the amplitude, changing the maximum displacement from 1 centimeter to 2 centimeter, then the period remains the same. That should say the only thing changing in the system. All right, take a second to pause this video here and write that down. When you hit play, take a look at the scoring guide. All right, taking a look at the scoring guide here, you got 1 point for saying the time is the same in both cases, or at least that is the correct answer. And if you pick the incorrect answer, then you get no points. And basically, for talking about the period equation, saying it only depends on the mass and the spring constant, or that the period does not depend on the amplitude. Take a second to pause this video here, write that down, making sure you understand all aspects of the scoring guide. When you hit play, take a look at the next problem. All right, let's take a look at the last problem here. Another experimental design, a nice rotational motion one. We haven't quite seen one just like this, and so I figured it'd be an important one for us to cover here as we wrap up the course. It says here, a disc-shaped platform has a known rotational inertia. The platform is mounted on a fixed axle and rotates in a horizontal plane as shown above. A student wishes to determine the frictional torque exerted on the platform by the axle as the platform rotates. The student has access to equipment that would usually be found in a school physics laboratory. The question says to describe an experimental procedure that the student could use to collect the data needed to find the frictional torque exerted on the platform while it rotates. What quantities would be measured and what equipment would be used for the measurements? Once again, there's a lot of different ways that you could do this. I hope everybody realizes that basically, though, the only way that you could do this is by using this equation, torque equals I alpha, or using this equation, change in angular momentum equals the net torque times the time. Now, there are a lot of ways that you can make the measurements needed to do this experiment. I chose to go with the most simplistic way that you could possibly do this because I have a feeling, maybe, that some of you said, well, we could just use a motion sensor and measure the angular velocity of this spinning wheel. You can't do that. Motion sensors can only measure the velocity of things that are moving in straight lines. The only way you could measure the angular velocity of a rotating object like this is by measuring the linear velocity of a point somewhere on the disk, preferably on the edge, and then using the relationship here between the linear velocity and the angular velocity. If you put a point here on the edge of the disk, you could just set up a photo gate and measure the velocity of the thing as it passes through the photo gate. That is possible. I decided to go with a little more of a straightforward approach. I said, in order to determine the frictional torque exerted on the disk by the axle, we need to measure the angular displacement and the time it takes the object to come to a stop from some initial speed. In order to measure the angular displacement, we simply need to count the rotations experienced by the object. In order to measure the time it takes the disk to come to a stop from some initial speed, we can use a stopwatch starting from the instant we begin counting the rotations until it stops. Take a second to pause this video here, write that down, adding any parts of this that may be missing from your own explanation. When you hit play, take a look at the scoring guide. Scoring guide for this part here says 1 point for indicating valid measured quantities and 1 point for a list of equipment and a plausible way to measure the quantities stated in A1. The basic idea that you hopefully realized in this problem is that they told you we already knew the rotational inertia of the object. So you really just needed some way to measure angular velocity or angular displacement and time. If the friction is really the torque that you're trying to measure, the torque due to friction, you could just force the hand of the problem, so to speak, by making the final angular velocity equal to 0. In my view, that's the easiest way to go about this. Take a second to pause this video here, write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, moving on to part A3. It says to describe the overall procedure to be used, including any steps necessary to reduce experimental uncertainty. You're asked to give enough detail so that another student could replicate the experiment. The scoring guide gives a bunch of different methods that you could use in this experiment. Here's mine. I said in order to measure the frictional torque exerted on the wheel, we must measure the angular displacement and the time. In order to measure the angular displacement, we must count the rotations of the object, which we then convert to radians. We can measure the time it takes for the object to come to a stop from the moment we begin counting the rotations. We can spin the disk up to some initial speed and begin counting the rotations and measuring the time it takes to come to a stop. After we convert the displacement to rotations, or I should say to radians, we can find the average angular velocity, which is just half of the initial angular velocity, since the final angular velocity is just 0. Since we know the rotational inertia of the disk, if we know the initial velocity, final velocity, and the time, we can calculate the torque. We spin the disk to varying initial angular velocities, ranging from slow to fast, to collect multiple measurements. Additionally, we can obtain more measurements from single trials by having 2 people count the number of rotations and 2 people with stopwatches to measure the times. These values can be averaged together for each individual trial. It's important to realize by using the change in angular momentum equation, the change in angular momentum equals torque times time. To measure the torque, then, all you need is I, omega final, omega initial, and T. We already know I. We can measure the time with the stopwatch. The omega final is going to be 0. So that means the equation is going to reduce to negative I, omega naught, over T. The basic idea is it's always going to be the case when you have here these kinds of decelerations, or accelerations for that matter, that the average velocity is just going to be omega final plus omega initial over 2. And so the idea here, I think, is quite simple. We force the final angular velocity to be 0, and by doubling the average velocity that we get from doing displacement over time, we've got our initial angular velocity. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. When you hit play, go look at the scoring guide. All right, taking a look at the scoring guide here, you got 1 point for a practical procedure consistent with the quantities in A1. That basically means nothing. 1 point for a plausible procedure that can be used to experimentally determine the frictional torque. That says very little. And then 1 point for indicating a valid method to reduce experimental uncertainty. Notice here there are 4 methods. Method number 1 is start the platform rotating and let it rotate freely. Use a feasible method for measuring the angular velocity at 2 different times. This, of course, would allow you to get an initial and final, and if you have the time interval between it, then you can use the equation I just talked about. You can apply a known external force tangent to the rim of the initially motionless platform. You can measure the change in angular velocity as in method 1. You can also measure the radius of the platform or some other valid measurement of the lever arm. Basically, that would involve you in using your external torque here, tangent to the rim, to make the wheel spin. Physics would predict how much the angular velocity should change by. Presumably here, because there's friction, it's going to be a little less, and you can use the difference to calculate the frictional torque. I think that method is way too complicated, though. Method 3 says to measure the torque needed to maintain the platform at a constant angular velocity and determine if the torque is indeed constant by measuring the angular speed at 2 different times and seeing if they're the same within experimental uncertainty. Again, I think that's absolutely insane. And then method 4 is basically what I said, with the platform freely rotating, measure the angular displacement over some time interval. I think you should measure the angular displacement over a time interval needed to allow the object to come to a stop. That makes your life a lot easier. Take a second to pause this video here, write that down, adding any parts of this that may be missing from your own procedures, depending on which method you chose. Make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, moving on to part B here. It says, describe how the data for measurements could be analyzed to determine the frictional torque exerted on the rotating platform. Now, I haven't talked about this in a little while because we haven't done an experiment like this where they literally just want you to measure something. But I think the slope idea works. I wrote if we take the equation delta L equals torque times time and we solve it for torque, we get the equation torque equals delta L over delta T, which we can rewrite as I times omega final minus omega initial over T. In order to determine the frictional torque, we can create a graph of I times the difference in the angular velocities versus time. The slope of the line at best fit on that graph will be equal to the frictional torque. In order to determine the initial velocity of the disk, we can take the angular displacement of the disk after we convert it to radians and divide it by the time. This will give us the average angular velocity of the disk, which we can then just multiply by 2. Since the final angular velocity of the disk is 0, to find the initial angular velocity of the disk, we just multiply the average angular velocity by 2. I think that works. It's pretty easy. You don't have to go too nuts measuring all sorts of complicated things. It's pretty straightforward. Take a second to pause this video here, write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, take a look at the scoring guide. All right, taking a look at the scoring guide here, you got 1 point for a valid expression involving the necessary angular quantity consistent with the procedure in part A. You get 1 point for explicitly or implicitly relating the calculated quantity to angular acceleration. Of course, you could do that by torque or change in angular momentum. And then 1 point for correctly combining the above two concepts in a way that would yield the frictional torque. Take a second to pause this video here, write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, moving on to part C, one of the weirdest experimental design parts of a question I've ever seen on a test, but I do think it is a nice, interesting thing to think about here. It says it is often assumed that the frictional torque between two surfaces is independent of their relative speed. Spoiler alert, it is. However, the details of the axle's construction are unknown, and it is possible that the frictional torque for the axle depends on the platform's angular speed. It doesn't. Does the experiment described in parts A and B depend on the assumption that the frictional torque is independent of the platform's angular speed? Yes or no? Notice it says here either answer may be correct depending on your experimental design. If you answered yes, describe which part of your analysis depends on this assumption. And if you answered no, explain how your analysis does not depend on this assumption. I wrote here, yeah. Since our experiment involves us naturally varying the initial angular velocity of the disk, because we can't really control it since we're just randomly revving up the disk, we're assuming that the frictional torque is independent of the angular velocity. Now, I wrote that which we know to be true part for you guys. I wouldn't write that if I was taking the test, because the whole premise of this question is like, maybe you don't know that. It's not, though. But that's an important idea here. We have assumed by changing the speed that that doesn't matter, because it doesn't. But we have made that assumption, so to speak. Take a second to pause this video here, write that down, adding any parts of this that may be missing from your own explanation. Of course, if you wrote something completely different, as they mentioned, it depends on your procedure, so that may not be necessarily wrong. You hit play, take a look at the scoring guide. All right, here you got 1 point for correctly relating the procedure in parts A and B to the assumption of dependence or independence of the frictional torque on the angular speed. And then 1 point for connecting the analysis to the dependence of the frictional torque on the angular speed. So basically, for just being coherent, what did you say in parts A and B? Is it dependent or is it not? And then basically why? Did you vary the speed naturally and just let it fly or not? That's basically the point here. Take a second to pause this video, write that down, making sure you understand all aspects of the scoring guide. And when you hit play, take a look at the final part of this question. And that brings us to part D, the last part of this question here. Briefly describe how experimental procedure described in parts A and B could be modified to determine whether the frictional torque stays constant as the angular speed changes. If no modification is necessary, state that explicitly. In either case, describe how the data could be analyzed to determine whether the frictional torque stays constant as the angular speed increases. Now, it should be pretty unsurprising based on my last comment to my last answer here, but if we are trying to figure out if the frictional torque depends on the angular velocity, our experiment is built for that. We're naturally changing the angular velocity. So I wrote here, no modifications are necessary. Since our experiment naturally varies the initial angular velocity of the disk, we can use the data from each individual trial to perform a calculation of the individual frictional torques over each interval. Instead of just setting up the graph and doing the line of best fit, we can just calculate the torque for each trial. That's really the only difference is in the analysis of the data. All we have to do is compare the values from each individual calculation to determine if the frictional torque depends on the angular velocity. Also, since our method relies on the deceleration of the disk, each individual trial tests this as well, since the angular velocity of our disk is continuously changing. It's kind of a double whammy there. It's an experiment within an experiment. Inception. Take a second to pause this video here, write that down. When you hit play, we'll take a look at the scoring guide, and then we will wrap this up. Taking a look at the scoring guide here, they gave 1 point for a modification that has any additional trial at a different angular speed, or correctly and explicitly stating that no modification is necessary. Notice if you came up with a procedure that sort of kept the angular speed constant, really all you had to say was, we'll just do it at another angular speed, and that worked. Of course, when you vary the angular speed naturally in your experiment, like I did, then you just have to say no modification. And then it says 1 point for indicating how the analysis of the initial or modified experiment could plausibly determine whether the frictional torque is independent of the angular speed. And with that, that is it for the course, or at least for new videos. As you hopefully know, if you managed to make it through what I'm sure was a super long video, I did not look at the clock when I started this. Tomorrow is the final exam. Friday will be used to just go over the final exam, and then your test is Monday. Your goal for today, besides watching this super long video, is to just study and get yourself into a proper frame of mind to take an hour to an hour and a half long test for this course. But with that, that's it for today. Have a good one, everybody.